Thanks for coming. So this is joint work with Nicole, Rob, and Alex. There's also a full version on the archive, which is much better than the conference proceedings. So I'll start with a simple motivating example. This is dynamic pricing. So let's say you have 100 apples, 80 oranges, and 70 bananas, and you want to price them. You don't know what the demand will be a priori. So the way you would go about doing this is you will have T rounds. In each round, you set some price for apples, some price for oranges, and some price for bananas. And some buyer comes with some hidden valuation for these things, and they'll buy some number of fruits. So that's the only feedback you get. And then the revenue you get is the number of items they bought times its corresponding price. And then once you're out of fruits, you cannot sell them anymore, so you stop. And your goal is to maximize the total revenue. Right? So the biggest challenge here is you have limited supply of fruits, and with that limited supply, you want to figure out what the right prices for each of these things are. So more generally, you're trying to maximize an objective, in this case, the revenue, and you're subject to some inventory constraints. And such things occur in like many applications, for instance, auctions, crowdsourcing, etc. And so we'll study this in a very generalized setting called as bandits with knapsacks. So bandits is a well-studied area. There are many textbooks written on it. Like I've stated a couple representative one. And so in bandits with knapsacks, it's a modification of bandits. The setting is as follows. You have K arms or K actions. In this case, you can think of them as prices. And then you have D shared resources. So these resources are shared across the arms, and each of them come with their corresponding budget. So you have B1, B2 up till BD. And we'll assume each of this is lesser than the number of time steps. Otherwise, they're not a budget. And then what happens in each round, the algorithm chooses an action 80 from one of the K actions. So we'll assume that one of the actions is always that you can skip around. So you can, so among the K actions, one is to skip around. And then once you choose an action 80, you observe the reward corresponding to that action, which is RT. And that is in 0, 1, and you assume, and you see the consumptions for each of the D resources corresponding to that action. And this is, again, we'll assume it's bounded in 0, 1. And if one of these resources is exhausted over your, while you're playing this game, you have to stop. So you cannot play once one of the resources is exhausted. And your goal is to maximize the total reward. Right? So the challenge here is that you're only seeing rewards and consumptions for just the actions you're playing. So you don't know what would have happened if you played some other action. So for simplicity, we'll assume that all the budgets are same. This is without loss of generality. You can kind of rescale your consumptions instead. And then the way these rewards and consumptions come from, that splits the landscape of problems. So if these rewards and consumptions are being sampled IID from some latent distribution, it's stochastic bandits with knapsacks. And if they're set by an adversary, it's adversarial bandits with knapsacks. And in this talk, we'll be looking at both these versions, but the main contribution is in the adversarial setting. So what is known? So stochastic bandits with knapsacks is kind of like completely solved in the sense that optimal solution is known for it. The general formulation and optimal solution was from this paper in 2013. And then since then, there have been like a bunch of extensions. More specifically, like bandits has a lot of extensions in various classes, like say convex rewards or contextual version. And many of those have been translated to the bandits with knapsack setting, and they've also been solved in the stochastic setting. Nothing is really known in the adversarial setting except some concurrent work. So if you're interested in that, I'll tell later in the Q&A section. And so just to set the stage straight, I'm sure many of you have seen this, but I'll anyway say it. So there are a few ways in which you can view feedback models, right? So the common way in which online machine learning community views this is there's this bandit feedback, which is you choose your action and you only see the outcome corresponding to the action you chose. And then the full feedback is you choose an action and then you see all outcomes of all actions. So you also kind of know what would have happened if you would have chosen other actions. And then on the other end of the spectrum is the online algorithms, which is kind of the bread and butter of TCS community, where you see, first you see the outcomes of all actions, and then you choose one. So you kind of know the present, but not the future. So as you can imagine, like bandit feedback is like the hardest setting, and online algorithms is the easiest setting. But then there are like kind of subtleties in what you compare against. In online machine learning community, you look at things like regret, and here you look at things like competitive ratio. But these are far more related than they are apart. Okay, so the main result of our paper and this talk is going to be an optimal algorithm for the adversarial bandits with knapsacks. We get it in both in expectation and high probability. In a second, I'll say what that means. And the key technique here is to reduce it, like to take a black box bandit algorithm which doesn't know anything about these resources and use that to get an algorithm for the one with resources. So the advantage of doing this is that we get all the extensions for free. So you don't have to like kind of study each of these extensions separately. So if it is known in the regular bandit world, it's kind of known now in the bandits with knapsacks world. So let's look at what makes bandits with knapsacks hard, right? So in bandits, kind of one of the key things is that if you knew everything a priori, the best solution is to play the arm with the maximum reward. So that is kind of the like the de facto thing in bandits. On the other hand, here's a simple example where in bandits with knapsacks, best fixed arm is actually not the best way to play even in hindsight. Even in hindsight, you kind of have to play a distribution. So the example here is that you have two arms. Let's call it arm X and arm Y. So arm X or arm 1 consumes the X-axis resource, and arm 2 consumes the Y-axis resource. And the budget for each of this is T over 2. So if you played any single arm throughout, you'll only get a reward of T over 2. On the other hand, if you played them alternatively, or like say played them with probability half, you can kind of get your reward to be T. So you can get a factor 2 better than playing just the best arm. So now the optimal solution itself looks much more complicated. And the other thing is that, so in bandit feedback, you're only getting feedback for the arm you play. So you kind of have to do exploration to get to know what would have happened if you played other actions. Here, doing that exploration will also consume resources, so you'll have to trade off that. And in general, adversarial bandits with knapsacks is even harder. So the reason it's even harder is as follows. So look at this simple example where we'll show that you can't even get any form of regret, and you can get only like a constant factor approximation ratio. And the example is as follows. So you have two arms, and you have one resource, and the budget for that resource is T over 2. So arm 1 has the following consumption. So you have two instances. So in one instance, both instances look alike up till the first half of the game. In the second half of the game, in one of the instances, you get very low rewards for arm 1. And in the second instance, in the second half, you get very high rewards for arm 1. So you're unsure whether you have to use this budget T over 2 for the first half or the second half. If it was instance 1, you should have used it up in the first half. And if it was instance 2, you should have used it in the second half. But then you don't know this until you play half the game. And that's where you lose like a constant factor. And then if you kind of make a more nuanced construction of the same thing, you can show that you cannot get anything better than log T approximation ratio. And this talk is going to be about how to get that log T upper bound. And so just to set straight on what the benchmark is, so our benchmark is going to be the best fixed distribution over arms. So if you see everything, if you knew everything about the world from time step 1 to T, what is the best distribution over arms that will maximize your expected reward? So that is what we are going to be comparing against. And just so that I'm sure everybody knows this, but what does competitive ratio and regret mean? So if you can write down your the expected reward of your algorithm as sum 1 over ratio times opt minus another lower order quantity. So we call the factor in front of opt as the competitive ratio and the lower order quantity as the regret. So for stochastic bandits with knapsacks, the ratio can be 1. So the goal will be to minimize regret. In adversarial bandits with knapsacks, I just said the ratio can only be log T. So the goal is to get that log T in the ratio. So I'll start with a new algorithm for stochastic bandits with knapsacks. So it's completely solved, but the key contribution here is that it's a very simple and conceptual algorithm. And the other thing is that we'll use this as a subroutine for the adversarial setting. So it has a bunch of steps, and each of these steps are kind of like well known, but the entire thing is to just put them together and get us the right thing which we want. So the first step is to kind of characterize opt. And what is a common way to do that in online algorithms is to kind of write a linear program and say that that linear program is upper bound on opt. So in this case, let's say you have outcome matrices M1 till MT. That is, an outcome matrix for a given time is the reward and consumption for all arms in that time step. And if you look at the expected value of this matrix, you can use that to construct a linear program. So the linear program is fairly standard. I mean, you will see this, you would have seen this in many other online algorithms as well. It's just trying to maximize the expected reward. And then, an easy analysis will show that like t times the optimal value of this LP is an upper bound on opt. So this is a very standard technique you use in online algorithms. And instead of comparing with opt, since this is larger, we'll instead compare with this. So if you have a linear program, you can write down a Lagrange function, again, a very standard notion. It's not too critical as to how exactly the Lagrange function is defined, but it's, you just have to know that it's a function of a primal and dual values of a linear program. And the critical property a Lagrange function has is that you can view it as a zero-sum game. So you can view it as a zero-sum game between the primal and dual solutions, or in this case, it's the arms versus resources. So player 1 chooses an arm, player 2 chooses a resource, and the reward of the game is just the Lagrange function evaluated at the corresponding actions. And the critical property we have is that if some x comma lambda is a Nash equilibria for this game, then x is an optimal solution to the linear program. So this is, again, a very well-known fact. We'll kind of use this fact for the construction of our algorithm. So using these two facts, the algorithm looks as follows, which is, again, a very natural way to go from these games to an algorithm. So let player 1 be controlled by some bandit algorithm. I'll call it algorithm 1. And there are like some examples. For instance, EXP3 is a specific instantiation of that algorithm. And algorithm 2 is another algorithm which controls player 2. And each time step, you play a repeated game. So algorithm 1 will choose an arm AT. Algorithm 2 will choose a resource JT. And then once those two make their choices, we have to give them reward and loss. And the reward and loss is just the Lagrange function evaluated at those 2 points. So there's some subtlety that you don't know the exact Lagrange function because Lagrange function was on the expected matrix. So instead, you give the realized value, which kind of looks in that box which I've mentioned there. So it's, again, immaterial how the exact expression looks like, but one thing to keep in mind is that there's going to be a parameter T0 there, which is T for this algorithm, but when we go to the adversarial setting, we'll set a different value to that T0. So that's going to be the only change to the algorithm when we go to the adversarial setting. And then you play the arm whichever algorithm 1 gives in your original problem. So this is going to be the algorithm, and it's fairly natural, like given these other simple observations. And we're going to use this critical theorem, which is, again, well known. So the theorem states that if you play 2 regret minimizing algorithms in a zero-sum game for like t time steps, then they're going to converge approximately to the Nash equilibria. Again, there's some subtlety, the fact that this is a stochastic game and not a fixed game. But it turns out that it's kind of a folklore extension of the same well-known theorem due to Freund and Shapire. And putting all these together, we get the following regret bound, which is that with probability 1 minus delta, the actual regret is upper bounded by this expression, which is kind of optimal in some worst-case settings. But compared to prior work, it's not optimal in every setting. So the prior work can get optimality in terms of for every opt B pair. So since we are giving a much simpler algorithm, we are losing on that, but it's only optimal in the worst case. And again, so here I've hidden all the constants. The archive version has like better constants, thanks to people in the room. And so the main part of this talk was adversarial bandits with knapsack. So how do we use this kind of setting to get it? So it turns out that this picture where I showed you, none of these hold. Like the learning in games, etc., fails miserably when the games are changing adversarially. But but still, like, we are able to get something out of it, and that something is as follows. So I said there was this parameter T0, right? So once we plug in a random guess for opt into T0, we kind of get everything which we want. And if you plug in that random guess, we get that the ratio, the upper bound on the ratio is D times log T against an oblivious adversary. And that random guess is again a standard way to guess things, which is that take the 0T interval and then partition into exponentially scaled buckets. So you have log T many buckets. And the analysis is completely different, but one of the key parts is to show that, like, if you choose this T0 correctly, then in that correct guess, you get what you want. And since there are only log T many such buckets, the probability with which you'll get the right bucket is 1 over log T. And that something is this, what I've written down as crux lemma here, which is that we show that for any parameter T0 or any guess T0, the reward is lower bounded by some quantity. And this is going to be important because this is only working against an oblivious adversary, and this will only get you an expectation. So we'll have a slightly more complicated algorithm that works against adaptive adversary with high probability, and that uses this lemma again and again for various values of T0. So it's kind of what I'm going to do in the next 4 minutes or so. So the algorithm which works with high probability against an adaptive adversary is a fairly complicated algorithm. I can't go over all details, but I'll go over some high-level ideas. So the high-level idea is as follows. So you are going to do the so-called doubling trick on this T0. So you start with a small T0, and then you invoke the main algorithm. And then at some point, you realize that this T0 is a bad T0, and then you restart with a better guess of T0. You double D0 and replay main. So the catch here is that T0 was supposed to be our estimate on opt, and you do not have enough information to estimate opt with bandit feedback. So what do? So you use IPS estimates on all the quantities you have, and an IPS estimate will help you get among the randomness of your own algorithm. It will help you get the estimates of what would have happened if you played other actions. So using the linear program on these IPS estimates, you estimate your opt, and based on this estimate, you change your T0. And this turns out to be the right way to do it, and then we can show that, like, once T0 hits the right scale of opt, you will get what you want to get. And again, the analysis is like super complicated, but one of the key steps in the algorithm analysis is to use that lemma for various values of T0. But since it's complicated, I will not go into any more details. And finally, extensions, as I promised. So if you notice that in this, in our algorithm, that's algorithm 1 can be any like abstract bandit algorithm. We never really used any properties of it other than the fact that it's regret minimizing. So if you have an algorithm for an X bandit problem, we get an algorithm for X bandits with knapsacks problem. And in prior work, like in stochastic bandits with knapsacks, each of this was like a new paper and new algorithm completely unrelated. So we kind of unify all of that in this framework. The only caveat is that this X bandit needs to work against adaptive adversary, which is a very strong requirement. So not all bandit problems have that yet. So I'll list some future work and stop here. So one of the future works to get this best of both worlds. So our algorithm looks similar in both settings, but it's not exactly the same. There's some technicalities. So one of the things to get is, can you get it where the same algorithm need not know whether a priori whether it's a stochastic or a adversarial setting, and you want to get the optimal bounds in both settings. And the other open problem is to get like logarithmic regret bounds, which is instant dependent. And finally, can you improve the dependence of D in the competitive ratio? So we have a linear dependence. What if you can either get it to log D or completely remove it? So that's another open problem. So I'll stop with that and take any questions you have. Right.
How crucial is that? Like, suppose I define a slightly different gradient where we are allowed to continue the game, but of course, like any resource you learn out.
So in the stochastic version, like the algorithms kind of like exhaust all of them in a smooth fashion. So I think it may not be too critical, but the only problem is like formulating it that way. There like a lot of things break in the analysis, so it's not even in the stochastic settings, like, so even though the algorithm is smoothly using all these resources, it's like the formulation itself is not too clear, right? So in the sense, our linear program is, for instance, saying that every resource has to be maintained. So one of these, like the way you're stating it, this may not be an upper bound. So at an intuitive level, yeah, like in the stochastic setting, it shouldn't make too much difference. And adversarial setting, everything breaks. So no idea at all.